Hi everyone, I'm Tommy Minyard. I'm Director of Advanced Computing Systems at the Texas Advanced Computing Center at the University of Texas at Austin. And today I'm going to talk to you a little bit about building an internal cloud. I want to put a little caveat around this. I'm an HPC guy. My background is all HPC. I have been a cloud skeptic. I am coming around to the cloud. It definitely has its purposes and usage. One other note, I have to say, if you do have specific questions, I'll probably have to put you in touch with the folks who did a lot of this work. I wasn't personally involved with the cloud work, but I can get you in touch with the folks who did. So from our point of view, we had a lot of researchers who came to us and had specific needs that we couldn't necessarily meet on our large production systems that are supporting a wide range of applications and a lot of users. Those are general purpose platforms. We had folks who wanted to do interactive graphical research environments, orchestrated heterogeneous science workflows, their own web applications. They just wanted some web servers that they could use to submit and run jobs, science gateways and so forth. They may have wanted specific operating system profiles or network architectures, or they may want to access newly emergent hardware that we're not quite ready to put into production systems. So from our point of view, we wanted to be able to support these needs and a lot of these external requests. And we want to deliver the same quality of service for these cases as we've done historically for HPC systems. So we started looking at the cloud and the different environments out there, and we kind of built up a stack of the cloud computing environment. So of course we have the software as a service. These are designed for the end users, delivered primarily as web to them. The next layer below that, we consider the platform as a service, and this is where a lot of the APIs fit in. These are the tools and services to help the code and web developers to deploy their applications on the systems. And then something that we've pretty much handled for the most part at TACC is the infrastructure as a service. We've been doing this for HPC. We build systems, we build production infrastructure that folks can use, but in this case, users can provision these services and stuff, not using something that we've already provisioned for them. So just to kind of give you some examples of software as a service, I mean, you see these a lot with portals, a lot of web server environments. We have a design safe discovery workspace that we deploy and maintain at TACC. There's their Airport, Jupyter Hub, RStudio, our TACC Viz portal and everything is basically a software as a service. You pretty much interact with it with web, point and click, familiar for many users of the systems that don't want to have to go and compile and run specific applications. But to be able to run a lot of those things, you need to have these APIs that can then interact with the infrastructure. And so we support several different APIs. Agave is probably the most popular one that we've been supporting, and it's been under development and funded by the National Science Foundation and runs a lot of our own cloud services that we build upon. But we also have a TAAS API, that's the TACC accounting system. Exceed, which is a National Science Foundation cyber infrastructure for the country, has an API. And then there's another one for another cloud service I'll talk about more, which is called Jetstream API. And then, of course, at the very bottom, you have your hardware provisioning. And we actually run 4 different clouds at TACC currently. So Roundup is kind of our internal cloud. This is really our production cloud. This is where our web services run. This is where we want to have 5 nines. We want to have maximum availability of the hardware. So we do pay VMware license costs to be able to run a VMware cloud. But these are the services that need to be maintained and really production quality. We then have our own OpenStack internal cloud that we allow for development purposes. Here, if folks are researchers at the university or some of our partners want to spin up a virtual machine instance, we can very quickly do it in our OpenStack cloud with images that we have available. The 2 that I'm going to focus a lot on today is Chameleon and Jetstream. And these are kind of a different beast. Chameleon is an OpenStack public cloud. This one actually scares me the most, being responsible for security at the center as well. We literally give the users bare metal. They do the bare metal provisioning. Unfortunately, it's also the system that we have the most security issues with in terms of open databases and things that fail a lot of our security checks. So we have to educate users on how to properly use it. But this is a place where users can actually do cloud research and deployment in a much more flexible environment, and they get full control over their nodes and their bare metal that they get access. Jetstream is more of a typical public cloud OpenStack environment in that we provide images. You get vetted images. You can spin up these images. These can be, different operating systems. Already have pre-built applications in them, whether it's Jupyter or RStudio. And this is actually funded as part of National Science Foundation as well, as part of the Exceed resources available. So let me jump into a little bit about Chameleon. The goal here was to develop a reconfigurable cloud testbed. Like I said, we offer bare metal provisioning for the users on this platform. And it's as close as we can get in our environment to letting the users have the servers in their lab. But the goal here is to provide reproducible experiments in computational science. We have partnered with several other groups around the country and with CERN to deploy and operate some of these environments. And what's interesting here is we actually have a bunch of heterogeneous hardware. So we have some FPGAs in this system. We've got some GPUs. We've got some ARM servers. We are looking at putting some NVMe into this environment as well. But it's a place where people can experiment with the new technologies and not necessarily have to have a real production resource, but they can look at it from a bare metal point of view. So to give you an idea, this is using all Dell hardware. What we did is we built what we call a standard cloud unit. It's a one rack, basically. One rack lives up in Chicago. University of Chicago was the lead for this project. But the bulk of the hardware is actually housed at our facility at TACC. So we have 10 of the storage racks, or 10 of the standard cloud unit racks up at TACC. And we have all the storage. We have the 3.6 petabytes of central file storage. And then, of course, a lot of the heterogeneous hardware also resides at TACC as well. So the standard cloud unit is basically a 48U. We have 42 Dell servers in it. We put in some storage servers in each of these cloud units. We have a Force 10 switch that's an open flow switch, so it's reconfigurable. And we do also have a subset of hardware that has the ConnectX-3 InfiniBand network on it as well. The infrastructure that is shared, of course, is the storage. We have 3.6 petabytes with a 100 gigabit connection between the sites so that we can move the data relatively quickly between the sites. And I did mention the heterogeneous cloud units. And some of these are still under development as we're still getting some of the new hardware in, like the most recent NVIDIA GPUs integrated into the system. So the idea here is, though, is not only are we doing bare metal provisioning, but we can also let users do KVM in standard cloud environments. But normally the workflow on this, though, is you have to come in and reserve the hardware in advance. There's no resource manager, there's no scheduler or anything along those lines like a typical HPC system. You actually have to reserve the hardware. And unfortunately, a lot of the hardware has been reserved for like the next 6 months. So we're quite full, unfortunately, on the Chameleon system, but we are still working with users and research groups to be able to take advantage of the system. So now I want to switch gears a little bit and talk about Jetstream. And Jetstream is our newest cloud resource. Again, this is more typical of what we would envision of the cloud. The bare metal, again, is I like to call it the Wild Wild West because it's pretty much a free-for-all in that users can do whatever they want on the hardware. On the Jetstream system, we actually impose restrictions on what images and what they are allowed to spin up in their environments. But the key is here we want to have an on-demand interactive computing and analysis environment that has configurable environments. The user does get control over their environment once they get provisioned on the hardware. We want to support, again, computational reproducibility. We want folks that have a very specific software stack or a very specific image that they want to run. We want them to be able to reproduce those results. And of course, ease of use. We want point and click on almost all of this. We want users to use their browsers and not have to figure out how to set up SSH clients and a lot of the advanced stuff that's needed for folks to take advantage of HPC. So the goal here is really to support the long tail of science. Not everybody can leverage the HPC systems. So it's for the researchers and scientists that really need between 1 and a few hundred cores, maybe right now, maybe for the foreseeable future, but of course not forever. They may want to fully customize the OS and configuration for their environment. We do support that and allow that. If they could be working with cloud-native software already and applications and workflows, stuff that doesn't fit on the HPC systems. And of course, they may want interactive mode for doing some of their computing and analytics. So, but it's also useful in a couple of other realms, and this is one of the areas that has been expanding. But we do run a lot of our science gateways on here. More and more folks are building gateways to be able to get the science and get the data out to users. These are very simple gateways in that you have point-and-click environments, and that I just want to run with this data set, upload it automatically into the cloud, go do the processing, pull this data back for me at the end. And then, of course, the cloud can then, as people come in and start to run stuff, we can then provision and grow the resources needed for the science gateway on the compute capacity. The other interesting thing that we've been doing this with is for STEM, for education. You may want to have a class or a research group that wants to create a reference VM appliance. They want their users, their students to be able to use this environment in their things. Could be running MATLAB, could be running some specialized stuff that, again, is not as well suited for HPC environments. What it does is it really minimizes the need for their own local IT support. They don't have to worry about trying to figure out servers and get environments for the users to log into. They can just basically get access to the cloud. And it does let us onboard students and introduce them to the Exceed ecosystem. So while they may not be directly logging into the large systems that HPC systems, they at least get a feel for the environment and get introduced to it. And some of these science gateways and cloud environments do actually submit and run jobs on the large-scale HPC systems behind the scenes. Users don't actually see it, but they, when they're doing big workloads that don't fit in the cloud systems, it'll offload them onto the bigger systems. So we're actually partnered with Indiana University on this. They have an identical set of nodes as we have at TACC. The University of Arizona is also a partner in this, in that they have some co-development work. In fact, our two environments at IU and TACC are the production environments. The University of Arizona is doing the development environment on their little bit of hardware that they have. So each host is a dual socket Intel Haswell processor. We do leave hyper-threading on for those folks who want to take advantage of it. We have 1 terabyte local disks in each of the nodes. Users do have access to a Ceph storage environment. We have 20 of these 730XDs per each of the cloud environments. And we are running Ceph on these. It's a Hammer specific version. And it's configured as OpenStack storage. So we have a couple of different flavors of environment that users can do. We have a very tiny, if you only need 1 core and you're not doing a whole lot of processing, don't need a whole lot of RAM or storage, we can spin up to 46 of these on a single node. If you need a little bit more power, well, then we have different other flavors that you then engage in to launch and run your job in the cloud environment. So, the storage is Exceed allocated. When you ask for a request of time or resources on the environment, you do have to request how much storage you need. And we do this with OpenStack volumes. We are looking at the object store environment, but again, this is kind of a work in progress still from our point of view. So to give you an idea, the user basically just interacts with a web interface. We use Globus authentication and Atmosphere API to handle all the services. The Atmosphere services actually will go and talk to each of the OpenStack clouds. But basically, all the user sees is this one little environment here. So when the user wants to go and just to break down to the components. So Atmosphere is the web application and middleware for providing the user-friendly environment. The Globus Auth, of course, does the authentication, allows us to do identity and access management. We do leverage the Exceed services for allocations and account management. They need to tell us who gets access to the different systems. I did mention Ceph, that's our distributed object store. So just to give you kind of a feel, I'm going to walk through a couple of slides of the environment. So basically, when you log into the environment, you get a dashboard. That's your dashboard. You can kind of see the resources in use at Indiana and at TACC. Some of the different instances that are up and running. You have your own history down here below of what you may have run in the environment. When you want to go ahead and launch a job, in this case, there's a couple of different projects that this dashboard is associated with. that they've been assigned to from Exceed. And then let's say you want to go spin up an environment. Well, you go look at the different images. Right now we're looking for just the CentOS images in the search environment. You can see different CentOS images available. You click on one of these, and it brings up a little screen, tells you a little bit of detail about the image, what's in it. In this case, this has the development tools integrated into the CentOS 672 image. And then you just push, oops, went too far. Then you just push the launch button over here to launch your instance. And assuming that there are resources available, you come in, you give a few details. You want what your instance, in this case, the person wants to run RStudio. Again, you have instances of what's in use and what's available. So you can kind of see what size you want to run at. And then once you launch your job, you can do everything through a web interface. But one of the big things is people still need to SSH into the nodes, and they don't want to have to worry about setting it up an SSH client. We actually do this from within the web browser. This is I think it's called Gate 1 web shell, but basically inside the browser you can do a full SSH session. So you don't have to try to educate your users on how to install PuTTY, or they may be running Windows or something, and this has been always a challenge. The downside is now they kind of have to know how to set up their SSH keys, and we actually handle that for them through the web interface, where you can specify your specific key that you're going to use to be able to get into the instances, and it'll populate your instances in it. And of course, you do need to enable SSH access if you want to get into your images. You do not have to. You can do everything through the web interfaces. So it's really, the idea here is that we have some programmable cyber infrastructure. And we support a wide range of different applications. Here's some of your automation, orchestration, and workflows. The stuff in green is what we call finicky still. It hasn't quite gone into production. We're still testing. The stuff in red is in development. The stuff in white is actually running in production. So I think we did get Kubernetes up and running well. And I know that they've been working on the Elastic cluster. I think I got another slide or two on that coming up. If you are familiar with OpenStack, you can go straight to the OpenStack API client. Jetstream is just like any other OpenStack cloud. It's scriptable, and you can list all your VM images in the OpenStack cloud. Here's the Elastic cluster. This is the one that's in development. We are working on basically the ability to launch Elastic clusters. In this case, this was a 3-node job with cluster storage available to it. So. And I'm running out of time. So what comes next? We are looking at Ceph storage and other software components. Most of that's all working, but we need to improve the software integration, and we're doing a lot more development after the post-acceptance of the system. There's still a few rough edges that we need to improve, especially those guys who want really detailed and access to certain features that we're just not quite ready to give them to. So. It did enter production in September, and we are working on more features and, like I mentioned, additional capabilities into the system. So let me just jump forward, and I got 1 minute left. But basically, the idea from us for building our own internal cloud environment is that now we can support a wider range of activities for our users that we can't necessarily support on the big production systems. This is important for us because we also have had researchers who've gone out and used AWS, and they're like, oh, it's so easy. And then they get the bill later on, and they realize, oh, crap, what am I going to do now? And then they come to us and say, hey, can you help us do this with university resources? And we have to go say, well, we got to figure out if this can fit. But for the most part, we've been able to support their needs with our OpenStack clouds. And we've been building standards compliance, web service APIs, and tooling to be able to integrate HPC, data, analytics, cloud, all together into one environment. We do envision, in fact, we've been doing this a little bit now, where users now can build their own virtual login nodes in our cloud environment. Our OpenStack cloud, we will actually let them get an image that looks just like one of our HPC systems. It's virtual. It doesn't have necessarily direct InfiniBand access to the Lustre file systems and won't give you the I/O performance. But if you're running a web interface or something that you want to be able to let users submit jobs, that's the best way. We can spin up a virtual login node. It's got the same software stack as all of our HPC systems. Users can do whatever they want on that virtual login node. They don't have to impact other users that may be on the general login nodes. So it's really a nice, flexible environment for us. And of course, we've been able to manage production, development, and research clouds based on the VMware and OpenStack environments. I have to say, I was a skeptic early on, but OpenStack has come a long way in terms of its deployment and robustness in terms of using it in a production environment. So with that, I will take any questions. Oh. Oh.
So on your Chameleon OpenStack implementation, have you experimented with the Ironic interface? Or
That's exactly what we're running on it right now. It's the bare metal Ironic, OpenStack
Okay.
Ironic version. So yeah, that's absolutely the one we're using.
So is that the one you pulled off of the GitHub source, or is that?
I would have to ask the guy who did the installation.
Or is that the SUSE Cloud 9?
Send me an email, and I'm happy to
get
that answer for you. All right, I know we're standing between you and the reception, so.
I do have a quick question. So how much of a moving target is it to support Jetstream? Because OpenStack is moving, Ceph is a moving target.
This is,
what is the sysadmin to VM ratio compared to HPC?
So the sysadmin, so for a cluster of the size of Jetstream, it's pretty much 2 full-time admins, whereas for a normal cluster, it'd be less than 1 person to maintain. The problem is, like you said, it's a moving target. There's new versions of this, there's new versions of that, and they deprecate stuff so quickly. You have to stay with the leading edge stuff, or you're not going to get support, you're not going to get any help on it. So it has been a bit challenging. One of the things we've been able to leverage is, since we have our own internal development cloud, we typically do deployments there first. Make sure it's all working before we put it on the production systems. And it certainly is more overhead. The good news is that once you get your guys kind of educated on the OpenStack and everything, their workload has drastically decreased. I mean, Cody, who's been running Chameleon, it's much easier for him now. But the ramp up was very hard. I mean, it was a lot of effort. So.
Well, Tommy, thank you very much.
All right.